Thank you everyone for joining us. This is our 24th session at Hackaday Quantum Computing class, and we have our fourth guest lecturer today. We're very honored to have Professor Chris Ferrie joining us. Just a reminder that all of our content is on the Hackaday Quantum Computing through Comics project. You can find all the materials and the drawings and PowerPoint slides, recording all there. As people who have been joining the class know, we spend from 30 minutes to an hour every Sunday on one topic. And we've been using the quantum computing documentation from Microsoft and the quantum katas for exercises. Since September, we started inviting some professionals, experts in specific fields to talk about their areas of studies. And today we have Professor Chris Ferrie joining us, teaching us about quantum tomography. Chris is a well-known author, and he is a professor in University of Technology, Sydney, and he's also part of the Center for Quantum Software and Information there. And Chris will be teaching us something about the internal working of quantum computers. And if you get a quantum device, how do you prove that it is actually a quantum device? So it's kind of a unique and mind-boggling problem that he will shine some light on today. And as many of you know, that Chris also is an author for many publications, including the very famous children's series book. You might have seen Mark Zuckerberg taking a photo of reading his book, Quantum Computing for Babies, for his baby. So Chris has this whole series of wonderful books that you should check out. I know a lot of you would like to buy his books for your children. And reminder, all of the recordings from today and past will be posted on Hackaday as well as my YouTube channel, and Hackaday has been uploading the videos on the Hackaday playlist as well. Just a reminder, next week we don't have a class. Thanks everyone for also joining late, especially people in Europe are staying up late for this. And thank you, Chris, for joining us super early in the morning on your Monday in Sydney. Yes, you got your coffee. Well prepared. And then next week we have a break. Then November 2nd, we'll have Dr. Michael Beaverland come to us to talk about quantum error correction. That's also one of the most interested topics from this audience. Okay, without further ado, I will give the presentation to Chris. Welcome, Chris. Thank you for joining.
Yes, thank you for inviting me. This should be fun. I'm excited to see your artistic interpretation of quantum tomography.
Yeah, we'll share.
Yeah.
And learn.
So, if you've read the abstract, then you'll know that I have a little story to go along with it. I'm imagining the audience here, some quantum hackers, some quantum programmers. You've played with a little quantum computing. I even suggested the idea that maybe you even ran an algorithm. So here I'm showing you the IBM quantum experience, and this is a teleportation circuit. If you recognize it, it's teleporting this state up here from the 0th qubit down to the last qubit, and the it's a Y rotation, just a particular state. I mean, nowadays, if you want to teleport something on a real quantum computer, you have to know what state it is you're preparing because you're the one creating it. In the far future, of course, we won't know what the description of states are. but today we need to know what they are. So I know that this is a 0 state that's been rotated by y, about the y-axis by pi over 4. And down at the bottom, let's see if I can prove this. So down at the bottom here, you can see this is the simulation. So this is exactly what should happen. When all the measurements are done on all the qubits, then I should see these probabilities down here. This is a simulation, so this is what ought to happen, and I went ahead and I ran this on IBM's real quantum computer. So if you use the IBM quantum experience, you can create an algorithm like this. This is a teleportation circuit, as I said, and I can click run up here. What happens, of course, is that you get placed in a queue, and then your job runs. And I did that in the morning for most of you who are in the US, last night for me, and I checked this morning, and it did run. So we can see that I was in the queue for not so long, for one minute, and it took 14 seconds to run. The circuit, that algorithm ran of 1,024 times, and these are the outcomes here. And you can see that just by eye, they're not the same as the theoretically predicted outcomes. So I'll just put that up one more time. So this was the circuit. These were the theoretically predicted outcomes down here, 21.33% and 3.66%, those two values. And what happens is, well, they're not too far away, but certainly not the predicted values. So what went wrong? Is there something wrong with the way I used this quantum computer? Is there something wrong with my algorithm? The answer is no. In fact, the problem is not on my side, it's on the side of the device. So the device is not perfect. So you've been hearing about in your introduction to quantum computing about what will happen, what ought to happen when we have perfect quantum computers. So I guess 2 weeks time you'll hear about quantum error correction, which is kind of the pathway to get there. But right now we're not at error corrected quantum computers. We have noisy quantum computers. So an acronym that you may have heard is NISQ, N-I-S-Q. That stands for noisy intermediate scale qubits. And what this means is that we have not large scale quantum computers. So those would be ones that you would run Shor's algorithm on to factor large numbers. And we don't have just small kind of toy devices anymore. We have intermediate scale devices that do something interesting from a scientific point of view, maybe not interesting from a applications point of view, but yet are still noisy. So they don't actually perform the circuit that you ask them to perform. And what I want to tell you about today is a very active area of research, broadly classed as quantum characterization, verification, and validation. So you may have also seen this acronym QCVV. And if you've used some of these open source packages, I know just because it was one of the first ones, I use IBM and Qiskit quite a bit. And they have an entire module within Qiskit for QCVV, and they use this acronym. But where it all started was this problem of tomography. So I'm going to tell you about a small piece and how that connects out to the big picture, and where sort of this characterization started. So if I am IBM and I want to improve upon what's happening here, I want to actually create a device that when somebody sends me this circuit, it actually happens as desired, then I need to characterize all the things that might go wrong, all the things that are going wrong in the device. So in if you're familiar with quantum circuits, then you'll know that time is going from left to right. So at time 0, I always start in the computational 0 state, and as I move right, I step through instructions, gates that are applied to the qubits. So at each point in time, the state of the qubit changes according to what gates are applied to it. So at each point in time, there's a new state, and in reality, there's a continuously changing state. And so this is potentially a very difficult problem. I may have to characterize some continuous time dynamics of some physical system. And where do those dynamics come from? They come from the things that I'm intentionally doing to it and the things that are unintentionally happening to it. And in principle, there's at least a weak connection between every particle that you're interested in and every other particle in the universe. So that's potentially a lot of things that you have to characterize. We're not going to do that. We're going to first start with the most simplest problem that we can imagine in this area, which is I prepare a state, say this state ry pi over 4 that I want to teleport, and I just want to figure out what state exactly did I prepare. So I suspect that I've prepared a 0 state and then applied a y rotation, but that might not have actually happened. How do I verify that that state happened? Or a little bit more sophisticated, how do I figure out what the state actually is after I apply that gate? All right. Okay, so there's a lot of names going around here, and the particular problem that we're going to look at is quantum state tomography. So again, this is asking the question, what is the state of the quantum data at some specific instant in time? So another way to phrase it is we want to read some quantum data. Okay, so let's just recall what this means. So state, you have seen this ket with a psi inside of it. I don't want you to think of that as something real and physical in the world. This is like an analogy with, say, a bit. So if I say I have a bunch of bits and this is like bits b sub 3 in some bit string, it has a particular value. It's either 0 or 1. That's its state. The psi is, in the case of the smallest unit of quantum information, the qubit, a particular two-dimensional vector. So this is some two-dimensional vector. One simple way we'll look at it later is like this. So it has two values, and those are two numbers, and the state is the particular two numbers that are currently specifying this quantum information. So it's a abstract thing, not necessarily a physical thing. Okay, so you recall that determining quantum states is, in some sense, not so difficult using linear algebra. So I start my computation in the 0 state, and then I apply some gates, and I end up at some new state. And to figure out what that state is, I just apply these unitary matrices, these quantum gates to it, and I've determined what the state is. If you're a physicist, then you just solve Schrodinger's equation and you find out what the state is. That's the process of deduction, and that's textbook quantum mechanics. In the lab, the problem is the opposite. It's the problem of induction. I don't know what the state is, and I can apply things that I know, and I can measure things in relation to the state. But what I end up with, remember I showed you, I actually ran an experiment on IBM's quantum device. And what I ended up with was just a bunch of data. So how do I get from the data that I observed to the state? And this isn't a uniquely quantum mechanical problem. So a simple example might be I have a coin, um, and it's got a heads, and you can help me out here, Kitty, and a tail. That's supposed to be a tail. Maybe that's I was imagining like a chipmunk tail. Anyway, so I have a coin, and maybe I want to bet on the outcome of this coin toss. So do I accept even odds? Well, I don't know. I don't know. Maybe the coin is a trick coin. Maybe it has a bias to it. Maybe it's a very slight bias so that it's not so obvious. Like I really simple to detect cheat coin would be one with two heads. But what if I somehow figured out a way to slightly bias the coin so that I could win just marginally, be like a casino? Um, so how do I determine what the bias of the coin is so I know what odds to accept in a bet? Well, I start flipping it, and here I've flipped, heads and then tails and then heads and then tails again, and so on and so forth. And say I flipped it, say 10 times, and out of those 10 times, I saw 6 heads and 4 tails. Is it a fair coin? Well, it could be. Certainly, the most likely outcome is 5 heads and 5 tails, but it's only marginally likely. It's, 6 heads and 4 tails and 4 heads and 6 tails, probably together. Those two together are more common than 5 and 5. So we can't actually answer this question. Even if I flipped it 100 times and just miraculously, or unmiraculously, it came up 60 heads and 40 tails. Now, I'm a little bit more confident that the coin is not fair, but if you've read about, if you read about, science topics in the news, you'll know that things usually come with these p-values. The p-value here is probably around 2%, which means that if the coin was a fair coin, then I would see an outcome this extreme 2% of the time. But still, if I played this game like a casino many times, then 2% of the time, even with a fair coin, I would see something like this. In fact, even with a fair coin, I might see 99 heads and 1 tail. So this problem is a very old problem and one that's still argued about today, which is when I see some data, how do I infer what the state was that generated that data? That's the problem of induction. And it goes back, thousands of years. A classic question that's related to this sort of binary hypothesis testing, Laplace asked, what is the probability that the sun rises again tomorrow? Can you assign that 100% probability? Only because you've seen it happen, I guess, I don't know how many days alive I've been, but I've seen the sunrise every day. So does that mean there's a 100% chance it'll rise again tomorrow? And philosophers still argue about whether or not that's the correct answer. Since I'm in probably the furthest Eastern time zone, I can tell you that indeed the sun will rise on the 19th of October. So no need to worry about that. So this problem is not a quantum mechanical problem. The problem of assigning some description to a probabilistic process given data is just a generic problem in statistics. It's the process of induction. So this is why this is kind of a difficult problem because in the opposite problem, when you have deduction, there's a unique answer, there's a correct answer. And in this case, there's no correct answer. And this is why many people argue about it. But we're going to assume that, you know, for free, whenever we perform a measurement, we don't have to consider this particular problem, because there's more interesting things that come up in quantum mechanics than just you know, the problem that arises that's equivalent to flipping coins. So when we perform a measurement, we're going to assume that the measurement just reveals these probabilities to us rather than some finite statistics that arise. And let me, in moving forward, for the time being, we're going to assume that there's no phase here. Okay, so the state is just this cosine theta over 2, sine theta over 2, and the reason that I want to do that is so that I can draw the state space as a circle. Okay, so I have my quantum state. Its particular location is given by theta. There's the 0 state up there. There's the 1 state down there. If you recall the plus state, which is a superposition of 0 and 1, and then the minus state, which is another superposition of 0 and 1 with a minus sign there. And the state is, the quantum state is just some particular location on this circle. So if you're familiar with what's known as the block sphere, then basically we've cut the block sphere kind of down the center of the x-axis. So there's no y-axis. So there's no y value. All I have is a z. So this is just if you're familiar with the block sphere, all I have is a z and an x-axis here. And the reason for this is just so that we can draw pictures in 2 dimensions and think about things in a little bit more simpler terms. So when I perform that experiment on my IBM device, remember that here what's happening is I'm measuring these qubits in the computational basis. So each qubit is measured and either a 0 state or a 1 state occurs. And so when I measure, I'm going to get only either this state or this state. So I have some state. Let's suppose it's the state that I've drawn here, right? So here's the state. Remember, we don't know what the state is. I've set things up in my quantum computer. I expect to be preparing this state here. Again, there's a physical device, and I want to encode some quantum information, and this is the quantum information that I want to encode on that device. And now I want to go and I want to read that quantum information. And again, we're going to assume that when I perform the measurement, you recall that it collapses to 0 or 1, and that probability in this picture is related to how close the state is to either 0 or 1. But we're going to assume that we get that number. Or another way to say it is, I can do an infinite number of measurements. Let's just assume that. And how do I do that? Well, I just in practice, I just prepare the system again and again and again. So that's what happens in the actual experiment. Those 1,024 shots, they were called, are just the experiment resetting itself and starting over again and performing measurements. So every time I run an experiment, I get a 0 or 1, and then I kind of collate all of this data. Okay, so here I have done an experiment, and I have my 1 state and my 0 state, and here's the state that here's the state that was actually prepared, which again, I don't actually know that that was the state that was prepared. And what happens is, so let's just run that state. So the state is psi, and it's cosine theta over 2, 0. Let me make that a little bit bigger and more clearly for you. And the rule in quantum mechanics is that I will see this outcome here with probability equal to the square of that coefficient in front of the 0 state. So I need to square this. So I have cosine squared theta over 2. That's the probability with which I see the 0 state. And if I performed this measurement, computational basis measurement, an infinite number of times, then the fraction of times I see the 0 outcome will be this number. Whatever theta is, it'll be that particular number, cosine squared theta over 2. But because of the square now, I have 2 different values of theta that are consistent with whatever number that ends up being. So when I perform a measurement, I kind of get the distance to that particular state. So if I perform a measurement of 0 and 1, then I get a number that tells me the distance to the 0 state, or equivalently the distance to the 1 state. So in this case, I don't know whether it's theta or minus theta because those give the same value of cosine squared theta over 2. Okay, so it seems like I can't actually solve this problem. I want to read the quantum information, but I can't actually do it because I can't distinguish between these 2 states. Well, this isn't the only measurement I can do. I can perform a measurement in any basis, and that means I can distinguish in quantum mechanics between any 2 orthogonal states. And if I'm going to do another one, then by symmetry, maybe it makes sense to do kind of this plus minus state. Also, it's the only states that are really have their own names. So let's use that basis. Okay, so now I'm going to perform another measurement on another infinite set of copies of this state. Remember, it's the state here. And at this point, I know that it's either this one or this one. And now when I perform a measurement in this basis, I'm going to get the plus state or the minus state. And I can calculate what those probabilities are because I know what the state is. So I could rewrite this state up here in the plus and minus basis if I wanted to, but like geometrically, I know that I'm going to get the distance to the plus state from this measurement. And what will happen is I'll know that it's either that state or a state that's the same distance away from the plus state, which is the one opposite kind of transpose or reflected in the x-axis here. So the 0 basis, the computational basis, tells me the distance to the 0 state up here, or how far away it is from the 1 state. And when I perform a measurement in the plus minus basis, then I can tell the distance to that state. And now you can see that with these 2 numbers, I can uniquely identify the state as this one here. So I needed to perform 2 different types of measurements because of this collapse rule in quantum mechanics. Okay, maybe that's a good place to pause and let anyone ask any questions. Kitty, how do we want to manage that? Do people just unmute themselves and that's fine with me?
Yeah, we can have people unmute or type questions in the chat. So I would remind people that this is very similar logic as the CHSH game. So if you've taken that class, if you haven't seen that, you can look at the past classes and find the CHSH game that's kind of using similar ideas here. Is there any question from the audience here yet? I actually have one.
Sure.
As we wait. So I'm wondering, how are we going to practically use this method in actual quantum circuit, for example? If we want to know the state at each point of our operation, can we really do measurement there? Because then we'll just, I hate to use the word collapse, but it is forcing a state to come out after the measurement. How do we get back to it then?
Yeah. So so there's a couple issues. So in this circuit that I'm showing you, there's a state at the end of the circuit. So that might be a state that I'm interested in. And what I would need to do is perform I'd have to repeat this circuit with different kinds of measurements to get the state at that point.
Mm-hmm.
And then I could move backwards. I could remove this and then do the same thing. And then I would find the state at one step prior. And then I could remove this and I would find the state after performing the same kinds of measurements. I would find what the state is at that point. And ideally, what I would find is like these numbers, the actual state vector, and then I kind of have to make some assumptions there. I have to assume that the circuit that I'm showing you here is the same circuit, it does the exact same thing up to that point for this new circuit that has an additional gate added to it. So there are a lot of assumptions that you have to make, right? So I have to assume that where this dotted line is, that I've prepared the state that was just shown, and so that when I add this new gate, I'm only modifying that previous state. So it is a difficult and challenging problem. I'll talk a little bit more about the various levels of difficulty at the end of the lecture. Yeah.
There are two questions in the chat. I think the first one's kind of, you've already answered it. So John asks, how do you measure the state twice if the state collapses after the first measurement? Right.
So you have to, I like this diagram here. So let's go here. So when I ran my quantum algorithm on the IBM quantum computer, what happened was that whole thing was repeated 1,024 times. So the state collapsed 1,024 times. The whole thing was re-prepared, starting in the 0 state. All of those gates were applied again, and the state collapsed again. So the first thing that should come to your mind is, I thought there was like no cloning. How do I make copies of the state I'm interested in the data that I'm interested in reading? Well, you can copy quantum information in a particular basis. And really, another way to think about the state is just a description of the preparation procedure. So in this case, the preparation procedure is this procedure here. And so I can copy the quantum data, whatever quantum data is output at the circuit, simply by starting in the 0 state and just applying the same gates. So if you can imagine that there's 1,024 different devices, and I apply the same thing to all of these devices. So I I apply this circuit to each of the 1024 devices. And so each of those devices should be described by the same state. So now I have 1024 states, and I can do these different measurements, these multiple measurements in your question, these two different kinds of measurements by just taking the first half and measuring in the 0, 1 basis, and taking the second half and measuring in the plus minus basis.
Great. And a question from PK. Usually in some of the tutorials, I have seen 0 and 1 states are shown in orthogonal vectors, but you are showing them opposite side of a circle. Oh yeah, you also explained it is basically projecting the block sphere into the 2D circle.
Yeah, that's one of the things that that I've always thought was unfortunate about the block sphere, especially when you're introducing it, is that orthogonal states are not orthogonal. They're antipodal states, and that I think if you think about it long enough, you'll see that it comes from this definition right here. So when the block sphere is defined, it's defined with this half, and the reason is quite simple. It's because if I didn't have the half there, then you're right. The 1 state would be over here, but then the 0 state would be at the bottom again, and I would kind of cover the sphere twice, or in this case, the circle. So in order to cover the sphere only once, then I divide theta by 2, so that it doesn't become orthogonal in Euclidean space, but they're still orthogonal in this complex 2-dimensional space. There's actually really interesting geometry there, but basically it comes down to this definition of theta over 2, so that the circle, or in the case of the block sphere, we're only covering it once rather than twice.
There are 2 more questions. Do you want to take them now or wait till later?
Sure, yeah, we can take them now.
Okay, so Daniel asks, is it correct to say that you can clone a known state, but not an unknown one?
Yeah, that's right. So if I know the state, so you can clone classical information. Classical information is any basis. So a basis, the most obvious one would be, so let's just go over here. The most obvious one would be the computational basis. So if I have many, in this case, if I have 3 qubits, then I have these 8 different states, yada, 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 all the way down to 1. And the labels of those states are just 3 classical bits. And so, of course, I can copy those, right? Because I know I can copy classical information. So I can copy a single basis. And if I know what the state is, then it is an element of many different bases. So you're right. If I know what the state is, then I can copy it. If I don't know what the state is, so if it's a superposition of these, then there's no fixed gate that allows me to copy that independent of what particular superposition it is. But if I know that superposition, then I can design the gate to copy it.
We also shown the proof of the non-cloning theorem in one of the previous classes you can look back to. Howard asks, this problem space is 2-dimensional. Is this solution also good for more dimensions?
That's a perfect segue to the next thing I want to talk about.
Great.
How long do I have, Kitty? So I see we're at 50 minutes.
Let's have another 10 minutes.
Perfect.
Yeah.
Okay, that's perfect. So the block sphere, remember, has sort of a y-axis coming out. So there's a y-axis here coming out. It's a bit too thick. There's a y-axis coming out of my screen, and the story there is the same. So if I perform a measurement in this new direction, then I get the distance to that that sometimes it's called the plus y state or plus I state. And there would be two states that are consistent with that. Well, if we add another dimension, and in fact, for each of these measurements, there would be 4 states that are consistent with each of those measurements. So it's hard to draw in 3 dimensions. That's why I didn't do it. So if I perform a y measurement, then there'd be four, at some point I would be distinguishing between 4 states actually, to be, let me just draw a quick picture here. See if I can do it for just one measurement. So if I have 0 and 1, and it's 3-dimensional now, and I say, what's the, I perform a measurement and I know the distance that the state is to the 0 state, that's going to give me a band, right? A band of states that are around 0. And if I then do X, then it's going to give me a band of states. And then those 2 things are going to cross at 2 points. One here and one on the opposite side of the sphere. And then you can imagine that that if I did the y measurement, I'm going to get a circle that's around the y-axis. And where all 3 of those rings coincide, that's the state. So it's kind of like triangulation, sort of a triangulation procedure. And remember that if I have more, so now I have a qubit. It has 2 dimensions, which if I can plot it on the block sphere are the block sphere is in 3 dimensions, but there's only 2 numbers, these 2 block angles. But I need 3 measurements to read, 3 different kinds of measurements to read the quantum data. In general, if I have n qubits, then the dimension d, so the number of complex numbers I need to specify it, is 2 to the n. And in fact, to read that data, I need something like, not exactly, but something like 2 times d different measurements. And so that's exponentially many different kinds of measurements for n qubits. And at this point, you might be wondering, what is the point of any of this quantum information stuff at all? If I can't even read quantum data, how, what is the point of encoding information in quantum data? By the way, the fact that a single measurement, so let's say one measurement or one type of measurement, or another way to say it is, yeah, let's do it this way. So if n qubits can convey only n bits of information. And this all comes down to basically this collapse rule, that when I have a qubit and I perform a measurement, the result of that measurement is a single bit. So if I have n qubits and I measure each of them, then I get n bits of information. And so it doesn't look like I'm able to kind of explore this exponential space, or, since this qubit is a sphere, I might imagine that I could encode a real number which has a continuously infinite state space. However, and this is actually a very interesting and deep question, and what the answer kind of shows us that quantum physics, like the rules that govern nature, sit right on the fence of like way too powerful and utterly useless. So if we could actually encode and read real numbers from qubits, then you can show from a computational standpoint that that quantum computing would be way too powerful. It would kind of upend everything we know about computation. And from a physical standpoint, we would expect to see that that effect in nature. So you have that kind of these restrictions on quantum data, and those restrictions are actually in some sense necessary so that we don't live in a kind of trivial world. If we if we were able to access kind of what we might naively hope or expect with quantum data, then trivialize kind of all of our understandings of computation and mathematics. Um, so that also means that our task in designing algorithms and coming up with clever ways in which these algorithms work so that the quantum data that we can read is accessible is a challenging problem. And you know, for scientists and engineers, problems are the reason that we're here. And um, kind of a we could go off on a meaning of life tangent, but we won't. Okay, so back to Kitty's original question. I want to draw kind of an axis here. And this axis is on this end is hard problems, like difficult to solve tasks, and over here is easy. And also, at the same time, this tells us like how many parameters. So over here is more parameters, and over here is less parameters. Okay, so on this side, let's say in the middle, like right around here, is what we've been talking about. State tomography. And I need to like 2 to the n parameters, where n is the number of qubits. If I wanted to understand also like the dynamics, so this is called process tomography. So if I wanted to not figure out what the state is, but figure out what one of those gates are, so if I have a unitary and I want to know what the unitary is, then I need, then it's not n vector, it's a 2 to the n by 2 to the n matrix. So I need 2 to the 2n. And I might want to know an entire gate set. And if I have, let's say, m gates, then this is m times 2 to the n, right? And, you know, if I wanted to understand kind of everything, and that's very hard and will require like infinitely many parameters, okay? So I think everything to the left of state tomography here is 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 necessary to start to try to build these prototype devices, the kinds that I ran my algorithm on at IBM. But you can see that because things grow exponentially, at some point we just can't do this. So if we have a device that can solve, you know, run Shor's algorithm, or even just a device that has 100 qubits, you can see that you know, 2 to the 200 is not going to allow me to actually characterize the gates that are being applied to this. So we need to go to the right-hand side. I will say that this has a name. This is kind of the characterization part. So we're trying to get a complete description of what's happening, or part of what's happening. Okay, so let's now zoom in. Let's zoom in here. And we can start to make assumptions. Okay, so the things on the left still requires some assumptions, but over here we're talking about more assumptions. So we might say that we have some special class of states. I was trying to think for a moment if you may have heard any in the previous lectures. And the idea would be you want to find a subspace of the full space that is not exponential in size. So you're looking for something that is like order n, the number of qubits. And if I can distinguish between those, then I can do this thing efficiently. And there's various kind of special classes of states, and that area is, you can think of as what the verification part. Verification. And then there's a whole class of different types of protocols that allow you to go all the way down to one. This has the name randomized benchmarking, which is a very popular randomized. Let's do it the English way. The S. Which tells us one parameter. And this one parameter is actually the parameter that you'll see here. So if so this is the device that I ran my algorithm on, the IBM Q Pagoda device. And here is the result of the, well, not the full result, but what their summary of the result of their characterization routine is. So when you look at the quantum devices that you're allowed to run on, you see them all here on the right-hand side. They're all in fact online. I was hoping that one of them wouldn't be online. So sometimes they don't show that they're online, and that's because the devices kind of shift and change. You know, these are experiments that are being run, and the kind of calibration becomes misaligned. So sometimes they go offline and they have to be calibrated. And during this calibration time, they're performing exactly this quantum state tomography and a bunch of other protocols, one of which is this randomized benchmarking protocol, which tells me the one number. And this is the one number that you see listed here as error rates. So it says qubit 0 has an error rate of 5 times 10 to the minus 4, which is very, this is one of their better devices. So that's very low. Some of the qubits are so the qubit 2 and 3 are half as good in some sense because they have double the error rate as the 0 and 1. And it also shows the error when I'm trying to perform these gates that make these qubits communicate. So that's typically a higher error rate, and you see that that we have 10 to the minus 3, or roughly 10 to the minus 2 actually, for the gates that happen between the qubits. So that's at the extreme end of characterization, where I'm getting a few numbers and I'm not actually figuring out what the particular state of the device is. I'm not reading the quantum data, but I'm getting some information about it. But it's not complete information. So that's at this extreme end, and this is the validation part of the QCVB validation. So I have quantum, characterization, verification, and validation. And so this, the kind of filling in this spectrum of hard and easy and figuring out all the details about each of these protocols is an extremely active area of research, because again, we don't have a device that is good enough to perform the algorithms that we want to run on it, to perform the gates we want to run on it. So we need to figure out what's actually happening so that we can improve in some sort of engineering cycle. And then I'll just mention the thing that I said that we forget about was the fact that in each of these, whenever you run these protocols, you're performing quantum measurements, and those are probabilistic. And so I've assumed when I've said these are the number of parameters that you need, or this is how difficult it is. Again, that's assuming that I get this sort of infinite number of copies. In the case of finite number of copies, we're back to this statistical problem. And it's not just a simple statistical problem like coin flipping. It's actually a new kind of probabilistic model. So you can think of quantum mechanics as a new kind of probability. And I looked this up just to give you a sense, because I didn't understand this until grad school, that academic statistics is a huge field. So the Institute of Mathematical Statistics, this is kind of an international governing body of statisticians, has 4,000 members, and there's probably hundreds of academic journals about statistics. And it's mathematics. It's people doing things that aren't necessarily thinking about applications. And what I did in a lot of my research in the past was in this mathematics and thinking about these new statistical models, and just trying to solve interesting mathematical puzzles related to them. So this small problem of let's read quantum data has spawned, an enormous new field of science, which has applications in building quantum computers, but also just in kind of recreational mathematics and thinking about probability and statistics. And if you're brave enough, you can even find people talking about this problem in the philosophy of science. So that's all I wanted. That's all that I kind of wanted to get across in this lecture. And if you have any questions about these topics, I'm happy to answer them.
Thank you so much, Chris. It's already been an hour, so if anyone has questions, make it quick. Yeah, it's a really great lecture. Thank you, Chris.
Oh, thank you.
I have a quick question, I hope. So the QCVB, is it only applicable for NISQ type of quantum hardware, or is it universal?
So my suspicion, well, we don't know. I mean, my suspicion is that at some point, when there's a job application available for quantum software engineer, at that point in time, the term tomography will be long forgotten, because if you have a large scale quantum device, then the reality is we just can't know. We can't open the box. We can't know what's happening inside. There's just too many numbers. So if there's 1,000 qubits, 2 to the 1,000 is just, I guess probably more than the number of atoms in the universe, right? So there's too many parameters needed to specify the state, and so this problem is not one we'll eventually even think about, and that kind of poses an interesting challenge, one that I don't think we've really kind of faced in engineering before, which is how do you build something that you can't even see what it is. In principle, you can't know what it is you're building. So how do you build it? So I think quantum computing, quantum technology is like a paradigm shift in the way we think about science and engineering. But I'm sure we'll find a way to get there. Now there's one, I think there's one area that some research that I've been involved in with some of my colleagues at Microsoft in this idea of bootstrapping. So this happens, of course, in classical computation, where the next generation of computer chips is designed by the current generation of computer chips. And actually, yeah, there's no human that really understands all of the connections that are happening inside of today's microprocessors. So why not apply the same idea in building quantum computers? So we build like IBM's devices. We have a great 5-qubit device. Let's use that to help us simulate and design the next device. So this is called quantum bootstrapping, and we have some kind of theoretical ideas for how we might make it work. So it's the same problem that I just discussed, but trying to utilize quantum resources to solve it, rather than thinking about coming up with descriptions that we can represent with classical data.
Right. Yeah. That's great. I think we should just pause there. And I think it will also make a very good connection to the next class by Michael Biberland on quantum error correction. So that's also a really complicated area. How do we make sure how do we correct the errors that's from the probabilistic outcomes? So thank you. And thanks everyone for joining us today.